synthesis-based ASIC design flow and methodology are illustrated in this video. The ASIC design flow using synthesis follows these procedures. The functional specification of the design is done. The HDL coding and VHDL in Verilog RTL. The RTL behavioral or functional simulation of the VHDL code. The logic synthesis, followed by test, insertion, and ATPG. Then the post-synthesis or gate level simulation, and finally floor planning and place and route. Follow the design of an I/O system. List the different types of I/O devices to be connected to the machine, and list the standard buses that the CPU will support. 2. List the physical requirements for each I/O device. This includes volume, power, connectors, bus slots, and expansion. 3. List the cost of each I/O device, including the portion of cost of any controller needed for the CPU. Record the CPU resource demands of each I/O device. It will include clock cycles for instruction used to initiate an I/O, to support operation of an I/O device, such as handling interrupts and complete I/O. CPU clock stalls due to waiting for I/O to finish using the memory, bus, or cache. CPU clock cycles to recover from an I/O activity. The range of caches from direct mapped to fully associative is really a continuum of levels of set associativity. Direct map is simply one-way set associative, and a fully associative cache with M blocks could be called M-way set associative. Cache represents the level of memory hierarchy between the CPU and main memory. In general terms, a well-defined cache will have the following parameters: the block line size, the hit time, the miss penalty, access time, transfer time, miss rate, and cache size. Porting the hard macros. For hard IP that was completely synthesized, the porting strategy is quite straightforward. We just resynthesize, targeting the new technology library, and repeat the physical design and timing model generation. For large macros such as multi-core embedded systems, where simulation speed in the system environment may be an issue, it can be useful to include cycle-based simulation and door emulation models. In general, RTL that complies with the coding guidelines will work with cycle-based simulation and emulation. However, test benches and bus functional models, unless coded to the same RTL guidelines, are important and effective for large macros. The product files, in addition to the RTL in Verilog and VHDL, we must include the synthesis and installation scripts. We include the reference library so that we can synthesize the design and verify that the installation was completed successfully. In addition, providing the reference library, scripts, and verification environment allows us to create this true environment. Verification files. The entire verification environment, including any bus functional models, bus monitors, or other models, and some set of verification test cases are included with this design. The integrator then develops a test suite to verify the functionality of the macros. So the bus functional models used to develop and verify the macro can be used by the integrator to create a test bench environment for the system on chip unit. The RTL was successfully developed for this ASIC/FPGA system. After functional verification, we also synthesize the unit into a gate level netlist. Then timing verification was performed to verify that the system on chip multi-core system meets timing requirements. Once the design meets timing goals, the netlist is given to the physical design, which places and routes the design, and then finally the chip is built and tested. The high-level system design process applied in this design was as follows. First, I identified the system requirements, followed by writing the preliminary specifications and parameters, thus developing a high level of algorithmic models in both C and C++ and also in VHDL. After that, I refined and tested the algorithms and determined the hardware and software partitioning at a system high level. Then I defined the interfaces. The software specifications were written to develop the prototype of the software. The hardware-software co-simulation was also performed. The hardware specification was developed with behavioral models. The partition was developed with reference to macro. The CPU design at its core uses a well-balanced pipeline coupled with excellent partitioning and mechanisms that compensate for increased pipeline latencies. This enables the use of simple and well-structured logic functions within each pipeline stage to achieve optimal synthesis. The synthesis-based ASIC design flow and methodology are illustrated in this video. The ASIC design flow using synthesis follows these procedures. The functional specification of the design is done. The HDL coding and VHDL in Verilog RTL. The RTL behavioral or functional simulation of the VHDL code. The logic synthesis, followed by test, insertion, and ATPG. Then the post-synthesis or gate-level simulation, and finally floor planning and place and route. The synthesis process was divided into two segments. The first segment employed a bottoms-up approach using design compiler in which all top-level blocks were synthesized using estimated constraints. Also, the layout process was completed. Here, the gate-level netlist is converted to a complete physical geometric representation. The first step was to do floor planning which is the process of placing the various blocks and the I/O pads across the chip area based on the design constraints. Then placement of physical elements within each block and integration of all analog blocks or the external intellectual property cores is performed. When all elements are placed, a global and detailed routing is running to connect all the elements together. Also, after this phase, a complete simulation was done to ensure the layout phase was properly completed. Finally, the file produced at the output of the layout is the GDS2 file, which is the file used by the foundry to fabricate the silicon. The layout should be done according to foundry design rules.